Dissolved gas analysis, or DGA, is a technique that's been saving the day for electrical engineers worldwide for decades. You see, transformers are secretly communicating with us through the gases they produce. They can tell us when they're not feeling well. DGA is the tool that helps us hear these whispers. It's all about understanding the gases dissolved in transformer oil. The presence of certain gases can indicate specific faults, helping us to nip potential issues in the bud, saving money. But DGA isn't just a cost saver. It's also a lifesaver for transformers, helping to maintain their efficiency and prolong their lifespan. It's the equivalent of a health checkup, keeping your transformers optimally prime. And the best part, you don't have to be a seasoned professional to interpret DGA results. With the right tools, anyone can become proficient in understanding what the gases are saying. And that's where the lab comes in. After this presentation, you'll have access to a free DGA interpretation tool, courtesy of learnoilanalysis.com. This tool will help you decipher the language of gases with ease, so buckle up, because we're about to embark on a journey into the world of DGA. We'll explore the different fault types, the key gases associated with each, and how to interpret the data. It's going to be a fascinating ride, filled with nuggets of knowledge that will empower you to keep transformers running smoothly and efficiently for years to come. So stay tuned as we delve into the different fault types and the key gases associated with each. Let's dive right into the world of dissolved gas analysis. Our first stop on this journey is partial discharges. Now, this is a type of fault that occurs within transformers, within the gaps of insulation such as an air bubble or small sections of the fluid, but not to allow continuous discharge between the metal contacts. Think of tiny storms within the oil. Hydrogen is the key gas here. Hydrogen is cut off carbon-hydrogen bonds and water molecules by these mini lightning storms within the oil. So, if you detect a rise in hydrogen levels in your DGA results, this could be a sign of a partial discharge fault. Now let's look at high-energy discharges and arcing. This type of fault is more severe than a partial discharge and suggests the electricity is jumping between metal contacts, causing a continuous arc. It's typically characterized by the presence of both hydrogen and acetylene. Arcing faults can be quite damaging and are often a sign of severe electrical stress within the transformer. Acetylene, in particular, is a potent indicator of arcing. It's a triple bonded molecule which suggests very high energy processes are occurring to break the oil and reform into a triple bonded molecule. It's important to note that both hydrogen and acetylene are produced by the breakdown of transformer oil, a process that occurs when there's an electrical discharge. So, while they're both key indicators of faults, they can also tell us something about the severity of these faults. It is also worth noting, mineral, natural and synthetic esters do show slightly different breakdown processes, so knowing the type of fluid will help in diagnosing the faults too. In a nutshell, hydrogen is a key sign of partial discharge, while the presence of acetylene can indicate a more severe high energy or arcing fault. Remember, early detection is crucial in preventing further damage and ensuring the longevity of your transformers. Hydrogen and acetylene are important indicators of faults, but there are more gases to consider. So, stay tuned as we continue our journey through the world of DGA, exploring more fault types and their corresponding key gases. It's a fascinating world, and we're just getting started. Continuing our exploration of fault types and key gases, let's focus on both high-temperature overheating and paper insulation breakdown. At the heart of our discussion is high-temperature overheating, a common defect that can seriously compromise a transformer's performance. When temperatures rise steeply, often due to overloading or lack of efficient cooling, fault gases are produced. They are classified according to temperature they form, typically grouped into less than 300 Celsius, 300 to 700, and greater than 700 Celsius. In a high-temperature fault, ethylene is produced, a double-bonded molecule indicating higher energy processes. This gas is a clear red flag for high-temperature faults, alerting us to a situation where the transformer's insulation system could be pushed beyond its limits. So when ethylene levels spike, it's time to roll up our sleeves and investigate. This isn't the only thermal fault gas though. Methane and ethane can indicate various ranges of temperature fault depending on their ratios when also looked at with ethylene. But what happens when the paper insulation in your transformer starts to break down? This is also seen when a high temperature fault is occurring, which is why we address it here, as it can burn the paper or cause carbonization of the paper. This is where carbon monoxide comes into play. Paper insulation is crucial for maintaining the electrical and mechanical integrity of your transformer. It separates the windings, provides a path for cooling oil, and even acts as a mechanical support. However, over time or due to high temperatures, this paper can degrade, leading to the release of carbon monoxide and eventually carbon dioxide. But since carbon dioxide is in air, carbon monoxide is easier to spot in a DGA test. This gas, therefore, is a telltale sign of paper insulation breakdown. Seeing a rise in carbon monoxide levels is a call to action. It's time to check your insulation for any signs of wear and tear, and perhaps add a Furans analysis to your transformer oil sample to both confirm paper breakdown and identify the way it's breaking down. It's quite fascinating, isn't it? By monitoring these key gases, we can diagnose potential issues in a transformer before they escalate into major problems. Ethylene signals high temperature overheating, while carbon monoxide points towards paper insulation breakdown. By keeping an eye on these gases, we can ensure our transformers continue to operate efficiently and safely. Remember, ethylene and carbon monoxide are key indicators of high temperature overheating and paper insulation breakdown, respectively. The presence of methane and ethane in the oil sample can suggest that a low temperature less than 300 Celsius or mid-range, 300 to 700 fault is in progress. To recap, thermal faults are classified by temperature ranges. The gas mixes can indicate which temperature the fault is occurring at. So, if you're analyzing a sample of transformer oil and you see high levels of methane, ethane or ethylene, you'll want to investigate further. These could be signs of thermal faults, which can affect the transformer's performance and lifespan. Remember, the goal of dissolved gas analysis is not just to detect faults, but to understand their nature and severity. By identifying the key gases associated with each fault type, we can gain valuable insights into the condition of the transformer and take appropriate action. Methane, ethane and ethylene are usually thermal fault related. You perhaps now understand we group faults into electrical or thermal with or without paper involvement. High temperatures or high energy produces more complex molecules that the lab can detect. Let's cover a type of fault that can have aspects of each. High energy discharges and arcing is often the most destructive and alarming, not least because it involves extensive damage and carbonization. High energy discharges, also known as D2 faults, are severe electrical faults within the transformer. These faults occur when there's a high energy spark, or an arc between two conductive elements. This can result from insulation failure, or even the presence of foreign objects within the transformer, including dirt and water. This type of fault is particularly dangerous as it generates a large amount of heat, which can cause major damage to the transformer's internal components. The heat produced can be so intense that it breaks down both the insulating oil and paper, leading to the formation of specific gases that are indicative of this fault type. When a high-energy discharge occurs, you'll see a significant increase in the levels of hydrogen, acetylene, and perhaps carbon monoxide. You may also see a drop in oxygen. We will explain why later. These gases are produced when the insulating oil is broken down by the intense heat. Additionally, as the paper insulation begins to carbonize under this extreme heat, carbon monoxide and carbon dioxide are formed, but also furans, which can be detected with a separate furans test. The presence of these gases in high quantities is a serious red flag, requiring immediate investigation and remedial action. Ignoring this could lead to catastrophic failure of the transformer, with potential safety risks and significant financial implications. So, in summary, high-energy discharges are severe electrical faults that cause extensive damage and carbonization within the transformer. They're characterized by high levels of hydrogen, acetylene, carbon monoxide, and carbon dioxide, and perhaps reduced oxygen, indicating the breakdown of both oil and paper insulation. Recognizing these signs early and responding quickly can save both the transformer and your pocket. High-energy discharges, involving extensive damage, are indicated by high levels of carbonization. Now that we've identified the key gases, let's explore the chemistry behind their formation. The processes leading to gas formation within transformers are fascinating and integral to our understanding of how each gas can be a telltale sign of specific faults. The oil-paper insulation system of a transformer is an essential part of this process. This system, when in optimal condition, ensures the smooth function of transformers. But when faults occur, the high temperatures and electrical discharges can lead to the breakdown of both the oil and paper, causing the release of gases. Let's delve into the chemistry of these reactions. When we talk about partial discharges, we're referring to the electrical breakdown of a small portion of the insulation system with, let's think of them as electrical scissors chopping off hydrogen bonds from both water and the insulating oil. This process leads to the formation of hydrogen. Now consider arcing. This is a more severe form of electrical discharge. Replace the electrical scissors analogy with a blender. Rather than a few gentle cuts here and there, it smashes all the oil molecules in its way to get from one electrical contact to another, and reforms into complex hydrocarbons. Here, the high temperatures cause the oil to decompose, leading to the creation of hydrogen and especially acetylene. High temperature overheating, as the name suggests, results from excessive heat. The high temperatures cause the thermal cracking of the oil, producing ethylene, similar to how a refinery manufactures synthetic lubricants, but in reverse. So think of high temperature overheating, winding back the clock and chemically changing a molecule into some of its constituent parts. When paper insulation breakdown occurs, the cellulose in the paper undergoes pyrolysis, resulting in the release of carbon monoxide as well as furans, although let's leave furans for another video. So high temperature faults produce ethylene, whilst low and medium temperature faults, on the other hand, produce methane and ethane. These gases form due to the slow decomposition of oil at lower temperatures. Thermal faults can also be classified by temperature ranges, with varying levels of carbonization. The type and amount of gas produced are indicative of the severity and nature of the fault. Lastly, we have high energy discharges, categorized by extensive damage and carbonization. Here, the oil undergoes severe thermal cracking and pyrolysis, leading to the release of a variety of gases. Remember, these are not isolated events. Multiple faults can occur simultaneously, or at least one fault can lead to others, resulting in a complex mix of gases. It's the art of interpreting these gas combinations that makes dissolved gas analysis so crucial for maintaining the health and longevity of our transformers. The chemistry of these processes is fundamental to understanding how each gas indicates specific faults. It's like a detective story where the gases are the clues leading us to the culprit, the fault. Understanding this chemistry helps us become better detectives, able to solve the mystery of transformer faults and take the necessary steps to ensure their smooth operation. Now, you might be wondering, how do we make sense of all these gases produced in a transformer fault? Well, that's where DGA diagnostic tools come into play. These tools help us interpret the data and identify the type of fault in a transformer. The first method we'll discuss is the key gas method. This technique focuses on the relative proportions of key gases and indicating the main ones at play. By examining the levels of hydrogen, acetylene, ethylene, methane, ethane, and carbon monoxide, we can gain insights into the type and severity of a fault. We have already covered much of these examples, such as acetylene linked with arcing and ethylene high-temperature thermal faults. Splitting the gases into electrical, such as acetylene and hydrogen, thermal, such as methane, ethane, and ethylene, and paper, such as carbon monoxide, helps at least begin to draw a picture of what's happening, albeit a bit fuzzy. Next, we look at gas ratios. This method involves comparing the ratios of different gases to each other. For instance, the carbon monoxide to carbon dioxide ratio can indicate paper involvement in a fault. A high ratio here might suggest the breakdown of paper insulation. On the other hand, the oxygen to nitrogen ratio helps us gauge the heating level within the transformer. Remember, I mentioned oxygen before. Well, the reason the oxygen can be relevant is oxygen is needed for oxidation to degrade the fluid or paper. A decrease in this ratio, meaning lower oxygen compared to its usual air composition, could suggest oxygen has been used up to oxidize the fluid or paper, usually by excessive heating. An interesting fact, the grandfather of modern gas ratios, Mr. Rogers himself used to work for our Learn Oil Analysis founder, Adam's father, in the late 1980s, early 90s. Small world, isn't it? Graphical methods also play a big part in DGA diagnostics. Another Goliath in the industry, Mr. Duval, invented the triangle and pentagon methods. These method plots key gases on a triangle or pentagon diagram to help identify fault zones. By placing the gases on this graph, we can see where they fall and quickly identify potential issues. Now, it's important to note that all these methods adhere to certain standards, such as the International Electrotechnical Commission's IEC 60599 and the Institute of Electrical and Electronics Engineers IEE C57.104. These standards provide guidelines for interpreting gas-in-oil analysis in transformers, ensuring that our interpretations are accurate and reliable. DGA diagnostic tools are an essential part of transformer maintenance and operation. They allow us to accurately interpret the data we gather, helping us detect faults early and prevent catastrophic failures. By understanding the intricacies of these interpretation methods, we can ensure the efficiency and longevity of our transformers. And remember, practice makes perfect. The more you use these tools, the better you'll get at interpreting the data and diagnosing faults. So, why not start now? After this presentation, you'll have the opportunity to try out a free DGA interpretation tool, courtesy of learnoilanalysis.com. Understanding these interpretation methods is crucial for accurate diagnosis of transformer faults. To conclude, let's recap the importance of DGA. Dissolved gas analysis is a vital tool in early fault detection in transformers. It allows us to monitor and address potential issues before they escalate, reducing downtime and maintenance costs substantially. Let's take a quick stroll down the memory lane. We discussed different fault types, including partial discharges, low and high energy discharges, thermal faults and paper faults. Each of these faults produce key gases, providing us with indicators for diagnosis. Hydrogen for partial discharge, hydrogen and acetylene for arcing, ethylene for high temperature overheating, carbon monoxide for paper insulation breakdown, methane and ethane for low temperature faults, and varying levels of carbonization for thermal faults. Remember the chemistry and processes behind these gas formations? The role of oil paper insulation and the chemical reactions that lead to the formation of these gases are fundamental to understanding how each gas indicates specific faults. We also shed light on the interpretation methods, the key gas method, gas ratios, graphical methods, and relevant standards like IEC 60599 and IEE C57.104 play a significant part in this. The ratios help us delve deeper into the nature of the faults. The Rogers ratio method and the Duval triangle method offer us useful aids for a comprehensive diagnosis. In essence, DGA provides us with a comprehensive, detailed, and accurate picture of a transformer's health, ensuring its efficiency and longevity. It's a fascinating field, one that combines engineering, chemistry, and a bit of detective work, all for the purpose of keeping our power systems running smoothly. Remember, a free DGA interpretation tool is available at dissolvedgasanalysis.com, a learnoilanalysis.com site. It's a fantastic resource for both beginners and seasoned professionals looking to deepen their understanding of DGA. Don't forget to like this video and subscribe to our channel for more insightful presentations. Thank you for joining us on this journey into the world of DGA. Stay connected, stay informed, and let's continue this learning adventure together.